Hello, my name is Alex Lee, and I will be presenting our research titled Measuring Fall Risk Using the Internet of Things Automatic Chair on behalf of my co-writers. And so for a little background, falls are actually one of the leading causes of injury and deaths in older adults, with the healthcare cost of falls totaling at over $50 billion a year in the United States. And so one commonly used test used to assess a patient's fall risk is the 30-second chair stand test. And so how one repetition in this test is constituted by is when a patient goes from a sitting position to a standing position, back down to a sitting position with their arms crossed over their chest. And what the 30-second test does is that measures how many of the repetitions a patient can perform within a 30-second time span. And so this test has standardized scoring, meaning that patients in certain age ranges have to perform a certain number of repetitions to not be considered at risk for falls. And medical staff will manually test patients for this test using a stopwatch to manually count the 30 seconds and by counting each repetition performed by the patient. However, the problems associated with manual measurements is that it's labor intensive, as it requires the observer to devote all their focus to counting the number of repetitions performed. It also only provides limited data collection because it's limited to only the number of repetitions that have been performed, and there's observer intervariability. And what that really means is that from observer to observer, each observer may time and count the patient slightly differently, causing discrepancies in measurement. And so there are existing electronic measurements that have been created for the 30-second test. Helmers et al. Developed a sensors belt, but the issue with the sensors belt is that first of all, it required a patient to wear a belt, and so this external device makes the test more cumbersome for the patient to perform. It also requires a stopwatch to time the test, making the test into a manual test rather than automatic, which essentially defeats the purpose of the device. Collado Mateo had participants wear a vest with metallic tape. However, the issue was that the participants had to sit in an exact position in order for the metallic tape and the chair sensor to be in contact in order for it to record. And so that's very cumbersome for the patient to perform, discouraging the observers and doctors from using this equipment. And so we came up with a solution in the form of our IoT chair. And so we wanted to allow for automatic sit and stand testing with our Internet of Things chair. You can see over here on the right, this is the chair. And so when we designed this chair, we had a few specific goals in mind. Firstly, we wanted to make it less labor intensive for observers to use. And we also wanted to make sure no devices were attached to patients in order for patient ease of use. We also wanted to allow for automatic measurements, meaning we don't want the use of stopwatch, which would allow for the observer to actually observe the patients themselves to see how they're performing. So for instance, rather than being forced to count how many repetitions are occurring, the doctor can actually see how the patient is performing during the test, in the sense that they can see the patient's facial expressions to see if they're indicating any pain, or they can see if the patient is visibly putting more weight onto the left or right side instead of just being concerned about the number of repetitions performed. We wanted to allow for expanded data collection in order to allow for the doctor to have additional information to analyze, which would allow them to better treat their patients. And we also wanted to provide accurate results at a low cost, incentivizing doctors to use this device and also allowing for widespread production. And so for the hardware development of the device, how it works is that essentially 4 pairs of weight sensors were obtained from bathroom scales. And so those 4 weight sensors are then mounted to a corresponding chair leg, because the presence or absence of weight on the chair can be translated into sit or a stand performed by the patient. Another 4 sensors are added to the circuit board, which can be seen over here. And all of these sensors are connected to the HX711 strain gauge load cell amplifier. And so what the HX711 does is I'll take the 8 sensors signals and it'll translate them into a larger and more usable digital signal to be used by our ESP32 microcontroller. You can see over here, this is essentially the brains of our device. It's the CPU with Wi-Fi connectivity. And so for the software development, the firmware was first developed using Arduino, and the data collection server was coded in Python before being ported over to PHP. And so essentially, how this process works is that the website will send commands to the ESP32 module via an MQTT broker. And so this MQTT broker here is essentially just a middleman in the process. It'll take that command signal from the website and it'll relay it to the chair's ESP32. The ESP32 gets the signal from the MQTT, and so then it starts collecting data using the weight sensors. And once the data of the patient performing the 30-second chair stand test is completed, it's sent to our server here. And then so from there, the server or the MQTT broker, either one can be used alternatively, is sent to the website for a doctor to view. And this website is secure. And so here's a little flow chart explaining how the process works again. So the chair sends a signal to the MQTT, relays it to the circuit board or the ESP32, and using the Arduino code, it sends it via HTTP post to our PHP server before displaying it on our secure website for a doctor to see. And so to assess the accuracy of our device, we ran clinical trials. We first obtained IRB approval from Azusa Pacific University. And so all participants who are included were adults aged 18 years and older. And the participants that are excluded were any adults who used a wheelchair or regularly used any assistive devices in walking, such as canes or a walker. And so how this clinical test worked is that we manually recorded the results, which is the more traditional method, while the IoT chair automatically recorded the results for the 30-second test, allowing us to compare the two results. And so we had 102 participants recruited, with 100 participants completing the 30-second test. And so here's a little video demonstration of one of these patient trials.
And then you sit back down.
This is the thing sometimes.
Yeah. You can take your time.
It hurts.
Yeah. If you can't do it anymore, you can always stop. So.
Okay.
You can stop.
Yeah.
And so you can see, so a doctor would access the trial that was just performed using their computer, and this is what they would see on their computer on our website. And so the IoT chair will automatically record the time in milliseconds. This is the x-axis of the graph that took for the patients to complete the cycle in 30 seconds for a 30-second test. And so you can see here each repetition. So the weight is displayed as the y-axis in 0.1 pounds. And so each orange dot roughly indicates a stand performed by the patient, and each green dot roughly represents a sit performed by the patient. And so using the dots or just looking at the cycles, the doctor can see how many repetitions were performed by the patient. In this particular graph, it's 8 repetitions. And this is all automatically created by our chair and transmitted to a website. And so one advantage of our chair is that it's actually able to show not only the total weight on the chair, but because we placed a weight sensor underneath each corresponding leg of the chair, we can show the pressure on each leg of the chair. And so this graph to the right, it shows in the purple line the total weight on the chair, but each other color line represents a different leg of the chair. And the green line represents the left front, the orange line represents the right front, the red line represents the left back, and the blue line represents the right back. And so you can see, a doctor would see this graph, And consistently, the left side, you can see the front in this case, consistently has more weight applied to it than the right side of the chair, which would be the orange line. And so the doctor is able to now show that the patient's been favoring the left side of their leg as they've been putting more weight on this portion of the chair. And so this allows the doctor to possibly interpret using this graph that the patient may have muscle imbalance, they may have muscle weakness in their right side, and that they're favoring their left side. And so another advantage of our chair is that our chair is also able to display the weight change rate, or the derivative in the weight change. And so it acts as a proxy of the patient's leg strength. And so you can see here, the derivative value is represented by this orange line here. And so higher weight velocity may mean that the patient has stronger legs, as they're able to apply more force to the chair in a shorter amount of time. And so that's what this orange line here represents. It's really just the change in weight over the change in time. So a larger value or a higher amplitude is more weight over a shorter period of time. And another advantage is that the doctor can see in the graph that we produced is the cycles between each sit to stand that acts as a proxy of patient endurance. You can see here, because longer sit and stand cycles may indicate increasing fatigue. And so what that means here is that in the graph you can see right here, in the beginning, the periods are relatively small, and they remain this. But towards the end of the trial, the patient has longer and longer periods between each sit and stand. And so what this could indicate is fatigue, as it's taking longer for them to perform each repetition. And so to compare the IoT chair and the manual measurements, what we did is that we took all the data that we collected during our test and we plotted it in the form of box plots. And so on the left is the observer recorded trials, on the right is the IoT chair trials. And so if you look at the two box plots, the 50% quartiles overlap with each other. And so in statistics, what that means is that these two data sets are not statistically significant. And from there, we can extrapolate that because they are not statistically significant, our IoT chair is as accurate as an observer would be. And so in conclusion, the observer and the IoT chair methods both produce similar results, as we have shown in the box plots. However, our IoT chair holds various advantages over the more traditional method, and that first of all, it's automatic and reliable. And what's so important about that is that through automation, the doctor can, as I said before, can focus on how the patient is performing rather than focusing on just the number of repetitions, so they can see in greater detail how the patient is really doing. They can see how the weight is distributed, or how certain aspects of the patient, like if they're attempting to hold on to additional objects for stability, they can all see that instead of just focusing on the number of repetitions performed. And it's also less labor intensive in that there's no stopwatch, and there's also no intervariability between observers, as having this chair will standardize all tests. Moreover, this chair was extremely low cost to produce. It only costed $60 to produce, and it's easy to use. The patients did not have to wear any external devices to perform the test, and the participants did not need to sit in a certain position. They can perform the test just as it has been traditionally performed. Moreover, an advantage of the IoT chair is that it allows for expanded data collection. We can show the rate of weight change on the chair, the weight on each chair leg, and the sit-stand interval time for each cycle. And so by doing so, we're able to provide so much more in-depth information that a doctor would typically be able to see. And now they have statistical evidence for when they come to a conclusion, instead of just relying on an eye test to say that the patient's staring their left side. They now have data that has been produced that shows that the patient is distributing more weight to their left side, meaning that their diagnostics are backed by additional evidence. And so this will really improve the doctor's ability to determine patients' leg strength and fall risk. And so this increased care will mean that fewer falls will result in decreased mortality and lower healthcare costs. Because remember, falls in the United States cost $50 billion a year. And so in the future, what we can do is that we can first program the website to automatically display the number of repetitions performed in the 30-second test. Because remember, as I showed before, we have orange and green dots representing a sit to stand. And so in the future, what we can do is we can just automatically display as an integer value the number of repetitions, making the website even more easy for a doctor to use. We could also refine the device for widespread clinical use. And so here's the references. And I'd like to thank you all for listening to our presentation.